This video introduces the joint HTCA multi-access edge computing solution from NoviFlow and Lanner Electronics. Hello, I'm Mark Leclerc, NoviFlow's VP of Strategy and Marketing. In this video, I'll be joined by Sven Freudenfeld, CTO of Lanner Electronics Telecoms Application Business Unit, and Jesper Eriksson, NoviFlow's VP of Product Management, who will describe our joint HTCA MEC solution, how it delivers a new architecture that revolutionizes the network edge, improves the security of the core network, and can reduce costs over traditional architectures by as much as 89%. First, we want to address a couple of things driving the transformation of network infrastructure and edge computing, and more specifically how this gives rise to the need for improved scalability and network programmability, and the impact on network security aspects as well. There is a strong trend in networks today for moving service processing closer to the edge. We see two major parts of the network edge being impacted by this trend. First, the customer edge, comprising mostly customer premise equipment, and we have the service provider edge. In the service provider edge, reducing latency, network flexibility, and the ability to dynamically change services are seen as key limitations to the effective deployment of virtual machines and the ability to scale services up and down in order to maximize price performance and reduce the cost of new service introduction. And speaking of costs, footprint becomes a major factor, as normally the deployment of edge infrastructure equipment is constrained by limitations in site space, power availability, and cooling capacity. As a consequence, the service provider edge is fast becoming the most dynamic element of the network's infrastructure in order to, 1, cope with the communication needs of many different types of devices, 2, with multiple different types of traffic, each having widely divergent characteristics, and 3, with many different types of services, each imposing their own requirements on compute capacity, response time, volume of storage, and networking. In addition, the response to the ever-increasing threat of cybersecurity breaches and denial of service attacks has significantly increased the complexity of delivering security at the edge. This complexity is becoming a limiting factor to protecting the network core, as well as a constraint on network adaptability, significantly augments traffic latency, and has become an impediment to service scalability. When you look at the overall evolution of fixed and mobile networks, the user planes are essentially coming together. We have also seen a trend towards the disaggregation of network functions, where services are delivered on hardware that provides a software-agnostic platform instead of the traditional purpose-built appliances or edge devices. The diagram illustrates a white box approach where we can dynamically scale multiple applications using the same hardware platform by integrating the network aspect. On the left-hand side, you typically see radio access devices, customer premise equipment, or multiple CPEs, as well as other IoT devices, which are connected via the aggregation side, typically using lower capacity links between 1 and 10 gigabits per second. The edge device thus becomes an aggregation point for these multiple feeds into the core network, and therefore there are some key functionalities that need to be supported by the service provider edge devices, either acting as virtual BNGs or virtual broadband gateways, or introducing some functionality like virtual EPC that is primarily software defined. The idea here is that we are introducing a platform which is 100% based on SDN infrastructure that provides scalability and programmability instead of the traditional edge devices at the aggregation point based on fixed function platforms with a network fabric that is neither open nor does it have any availability or programmability. Another need that we see at the service provider edge is for greater flexibility and improved programmability to support dynamic route flows in the platform. We also need to be able to bring compute resources directly to the edge, as we're doing some of the processing right at the service provider edge before passing the traffic on to the regional or core network infrastructure or the data center. These are the needs that we aim to fulfill with this architecture, using standard commercial off-the-shelf hardware and really driving it forward to deliver an agile, customer-defined infrastructure that can implement multiple virtual network functions on the same physical platform. And now, Sven and Jesper will describe the joint Lanner and NoviFlow MEC solution.
So what we're offering is the Lanner HTCA 6600 family, a second generation Xeon Intel scalable compute platform supporting up to 336 cores per device and advanced data plane programmability using the latest Barefoot Tofino, a member of Intel's switch fabric family, in a fully redundant configuration, which means the platform provides high availability and introduces network programmability right into the edge. From a software perspective, NoviFlow is delivering a mature network operating system and software to manage the platform, as well to deliver optimized networking services into the platform. Here I'll ask Jesper to add a few words on the platform software.
Yeah, NoviFlow is contributing two of its software products to this Lanner NoviFlow MEC solution. The first one is the NoviWare, which is a P4 programmable NOS for the switchblades. And the second part is CyberMapper, which is an application providing load balancing, packet brokering, service chaining, and end-to-end overall HTCA platform management.
NoviFlow software is basically addressing both the data plane as well as the control plane functions. The hardware and software elements of the platform come together to offer a genius SDN solution that not only provides the capacity to execute compute loads, but in a single packaging and delivers the control and networking functions into the same platform that makes it possible to significantly simplify the network architecture at the edge, lowering the cost, making the platform in particular advantageous to deploy in use cases and use case scenarios which are limited in space, power, or remote locations. There are some use cases where we have multiple dwellings which are acting as an edge compute device location, where we can provide dynamic server scalability as tenant needs to evolve. It's a single platform without any need for special cabling wiring, special wiring, or even making separate provisioning for the platform for as compute, networking, and storage are pre-integrated into the device. Also, since we are using a software-defined approach, we can basically scale up and scale down the application based on the need. At the edge compute side, we are providing load balancing, traffic mitigation on the platform level itself, traffic mitigation for security, including secure and virtual network functions at the edge, and then from the platform management point of view of using tools which allow us to remotely manage and provision the platform without the need of dedicated truck rolls or technicians to go on site to do the cabling and wiring or troubleshooting. We have an infrastructure in place which allows provisioning of services in a matter of minutes and removing the cost of additional truck rolls and the need for physical interaction at the edge platform and the edge resources. The second portion, because it's an integrated platform in which we have provided a lot of compute resources, we can introduce service chaining. With service chaining, we can bring multiple functionalities into the edge computing platform. Scalability is also a key advantage here compared to the standard 1U rack server architecture with a dedicated top-of-rack switch and dedicated stackable servers. Everything is fully integrated in our case and managed by a single device, which makes it simple to run. This is a significant cost saving. From a physical point of view, we have a modular approach where we provide everything fully integrated. We're using the Intel Barefoot Tofino switch fabric, redundant switchblade to support high availability functionality. The platform operating system and management system comes from NoviFlow. As we have compute nodes, one important factor here is that on the compute node is that we have a lot of lower networking graded feeds to connect to end devices like universal CPEs. The typical standard servers from other vendors do not support the granularity of ports, other than you have to buy additional network interface cards in order to accommodate that. From a single point of view, it's a pretty dense platform, so we support up to 336 cores into a 6U appliance. We provide networking interface cards built into the platform, into the compute node. And the total number of compute nodes is 6, plus the additional networking. And then, of course, the switch fabrics are based on Intel Barefoot Tofino, providing programmability and inbound telemetry, which makes it makes the filtering decisions right at the edge, and also addressing cybersecurity aspects and mitigation at the edge. The second aspect is the programmability, and to program the network interfaces as part of the SCN infrastructure, we're using a P4 and P4 runtime as a control fabric for the NoviFlow CyberMapper. Therefore, it provides a great deal of flexibility. It's open, programmable, meaning the entire platform can be repurposed via software to support multiple applications, so we can support multiple traffic handling functions and networking roles with the same chip. In addition, we have introduced a timing card, typically used for applications where we would provision PTP or IEEE 1588 support in order to synchronize packets from the fabric silicon itself.
Okay, thanks, Sven. Yeah, so as I mentioned earlier, NoviFlow is porting 2 of its existing software products to the Lanner HTCA platform. The first one is the NoviWare NOS that we're porting to the HTCA switchblades, the Tofino-based switchblades. And the second one is the CyberMapper, which is an application that we're porting to the HTCA compute blades. A little more detail on NoviWare. It's a mature SDN switch NOS that has been in commercial operation with a number of carriers since 2014. It has a full range of modern O&M interfaces, such as GNMI and GNOI. It supports the P4 runtime and OpenFlow 1.5 northbound interfaces. And these interfaces are used to configure and dynamically updating the packet processing in the switchblades. And they essentially allows the application programmer to define a unique match action pipeline to match the requirements of the application. Over on the right side, CyberMapper is an application built on top of NoviWare. It's in commercial operation with multiple carriers. And CyberMapper provides the following services: a sticky and stateless load balancing, traffic filtering and redirection, service chaining through SRv6, and more about these later. And then the visual operational analytics and telemetry. What this does, it collects data from all the various sensors and log files in the system, including the switchblades and the compute blades, and dumps it into a time series database. And this may later graphically be displayed for troubleshooting purposes. The visual telemetry uses INT that Sven mentioned earlier to measure latency through the various VMs being load balanced. And this also is dumped into the time series database and then may be later graphically displayed for troubleshooting. And finally, CyberMapper will provide the user with a complete picture of what's going on in the HTCA platform, an end-to-end view of the overall system. Next slide. This is shows the next layer of details on the NoviWare NOS. And as I mentioned earlier, NoviWare may be run either in OpenFlow or P4 runtime mode. And what you see there also is a number of management interfaces, such as GNMI, GNOI, gRPC for programmatic CLI, netconf. And then you see security being built into these various interfaces using SSH, Secure File Transfer Protocol, TLS, and AAA. And then in-band network telemetry, including the postcard capability, is also supported in both OpenFlow and P4 runtime modes. And then the user may put their own applications on the switch host processor through the KVM hypervisor that you see there too. And then, of course, statistics may be collected through the OpenFlow interfaces, SNMP, CLI, and INT interfaces. So that's more detail on the NOS. So moving to the next, here's some additional detail on the CyberMapper. So CyberMapper supports a number of use cases, and the first use case is this threat intelligence gateway. So a threat intelligence gateway blocks bad traffic based on prior knowledge. For example, filtering traffic based on URLs provided by the Internet Watch Foundation. And this is one use case that's in operation, commercial operation with a tier 1 carrier, mobile carrier in the world. Moving on to the next layer of functionality, CyberMapper also has load balancing for scaling out of security services. And then the packet brokering allows the user to use various filter rules. And in the HTCA use case, CyberMapper will load balance a cluster of virtual security appliances running on the 6 compute blades. And you might dynamically scale the number of virtual appliances up or down with a minimum impact on the state of the cluster, of the VMs in the cluster. One key feature of the CyberMapper is that it can offload some of the packet processing of the virtual appliances running on the x86 compute to the Intel Tofino silicon chip. And this capability will provide a major boost in the throughput capacity of the HTCA platform. Here's another illustration of CyberMapper, the use cases for CyberMapper. So what you see here on the left is a typical edge of a carrier or a large enterprise today. You know, it's complex, static, fragile, and expensive. It uses switches, packet brokers, and load balancers to steer and load balance the traffic through the various security appliances. On the right shows the same security functionality by using the NoviFlow CyberMapper. So CyberMapper replaces the switches, the load balancers, the packet brokers. It also replaces the T's that you see in the left picture, you know, representing a separate tap and monitoring network used for service assurance. And the way CyberMapper does it uses in-band network telemetry and monitors the performance of the appliances that it load balances. In the case of Lanner HTCA platform, the appliances are, of course, virtualized and run on the 6 compute blades. Here, I'm illustrating the high availability functionality of the Lanner NoviFlow platform. And CyberMapper has multiple levels of redundancy built in. The switch blades are duplicated and operate in active-active mode. Traffic from the outside is load shared across the 2 switch blades using lag. So if one of the switches fail, the traffic is redirected to remaining switch blades for the remaining lag group members. And the CyberMapper application runs on 2 different compute blades in the platform in an active standby mode. And then the last part, virtual security appliances or virtual network functions, they run in the compute blades in an N+1 or N+2 or N+N mode. And if one of the VMs fail, the traffic is redistributed across the remaining live VMs. Moving over now to the MEC use cases. The first use case I want to talk about is scalable security perimeter. And the HTCA platform may be deployed as a bump in the wire or as a routable member of an SRv6 network behind the edge router. What this means is that the security services are either hardwired into a particular location or globally addressable through the router network. And with the compute resources available on the Lanner platform, we estimate the following throughput performance. More than 700 gigabit of throughput for a firewall application, more than 300 gigabit of IPS, more than 250 gigabit per second of firewall plus IPS. The next use case is a virtual BNG use case. And this use case is architecturally different from the previous scalable security use case because here the subscribers are connected to the HTCA platform through an I/O blade on the front. And the I/O blade is connected directly to the compute blades running the virtual BNGs. So there's no load balancing needed. But once the BNG has processed the traffic, it is sent to the switch blades and for further forwarding in the network. So CyberMapper in this use case performs aggregation of all the traffic from the virtual BNGs running on the compute blades and traffic steering of traffic coming from the network to the virtual BNGs going out to subscribers. And with the compute resources available in the Lanner platform, we estimate up to 720 gigabit per second of throughput from up to 768,000 subscribers. The next use case is the SRv6 service chaining. And traditionally, security appliances have been hardwired into a specific location and only available for traffic going through that location. SRv6 opens up a new way of programmatically inserting security services in traffic flows that are not tied to a specific location. In this use case, the Lanner HTCA platform with NoviFlow CyberMapper operates as a security services proxy in a routed SRv6 network. A source router on the left in this picture, entering the edge central office, will insert a segment or SID in the service chain representing the security services it wants the packet to go through. And then it sends the packet to the next hop. Once the packet has been forwarded to the HTCA platform, the NoviFlow software will map this SID into a specific chain of security services. I think on the picture we show DDoS and IPS, and it could be any chain that the user may want to program. And then what happens is that the platform will execute these security services before forwarding the packet to the next hop. And Lanner and NoviFlow are working with a major North American carrier and a tier 1 router vendor to build this solution end to end.
I would like to elaborate a little bit more on the VBNG portion what was mentioned earlier in one of the use cases. The way with the physical hardware platform is architected is that each compute node has many of the networking cards or NICs built into the platform. So we are able to run the virtual BNG network function as an integrated network function on the compute board. And it becomes an aggregation point. And in that case, we pass the traffic onto a higher level traffic flow using the Barefoot Tofino switches as the traffic steering and load balancing for some of the security functions. As a consequence, that makes it very scalable, considering that we have up to 6 compute nodes and multiple resources available within the platform, and we can deploy virtual BNGs to accommodate very small to a very large number of deployment models. By introducing programmability at the edge as a switch fabric, service chaining is also brought onto the platform, so we can pass traffic onto another dedicated compute node or even another hop in the network edge to do processing with the exact next available compute resources in the network. This diagram shows that carriers are able to provide different compute resources at different locations at any given time. On the left side is typically the customer premise equipment or universal CPE, which is limited in resources from a 2-core all the way up to the 8-core. Applications may be balanced also into the edge central office, where we can offload the compute resources from the universal CPE towards the edge compute location, and therefore reducing the overall cost for customer premise equipment. This will be a balance at the edge where compute resources are allocated and being made available. Now let's take a closer look at the OpEx and CapEx scenario in this case for multi-access edge computing deployments. First, we wanted to showcase the equivalent on a typical deployment and configuration. On the left-hand side, you can see the traditional purpose-built appliances in a rack connected with cabling, wiring, and patch panels to accommodate up to 336 cores of virtual machines into the same platform. And in order to bring this to a software-defined scenario, we basically included load balancing and also load distribution to distribute traffic and VMs throughout multiple servers. On the right-hand side, you can see the combination of a NoviFlow Lanner multi-access edge compute platform, where everything is integrated. We provide the equivalent of the compute resources, as well networking and load balancing. So right off the bat, there's a big difference in price. The total software and hardware needed to deliver this platform on a traditional platform is about $2.1 million, compared to a scaled-down version with everything integrated and manageable down to $236,000. It's a significant cost reduction, and it's roughly about 11% of the traditional cost. A more visible difference is, of course, the size. On the left side, you see sort of a 44U rack type of deployments compared to a deployment with the redundant UPS up to maximum 12U. That's a main significance in reducing the footprint, which makes it very efficient for an edge compute and platform for edge compute devices.
Thank you, Sven and Jesper. So to summarize, the Lanner HTCA 6600 all-in-one scalable MEC platform leverages the most advanced high-performance processors from Intel, including the Silver Lake Xeon on the compute side and the Barefoot Tofino high-performance programmable network fabric. It delivers storage, compute, and networking in a single 6U platform, giving it a 4-to-1 density advantage over traditional modular MEC solutions. The platform provides significant performance advantages by integrating key network functions such as load balancing of VNFs, packet filtering, and flow redirection directly on the dual redundant terabit per second capacity network blades. By pre-integrating compute, storage, and networking in a single chassis, the Lanner NoviFlow MEC solution greatly reduces cabling costs and complexity, as well as eliminating the need for expensive truck rolls when reconfiguring or maintaining the devices. In terms of installation, the all-in-one design is ready to deploy, with the mature NoviWare NOS featuring sophisticated analytics as well as key VNF enablers such as service chaining and flexible networking that enables a wide variety of deployment scenarios. The CyberMapper control software delivers load balancing and optimizes the use of a wide variety of cybersecurity, VBNG, and other VNFs from leading ecosystem partners, supporting the most common use cases. Finally, the flexible and programmable network fabric is software upgradable to support functions and protocols that don't even exist yet, and leveraging the powerful P4 language to extend the functionality of the fabric as customer needs and network usage evolves. One last point to mention is the savings. Of course, up to 89% savings in capital expenditures and significant reductions in operating expenses due to the all-in-one design. You can get more information by going to www.noviflow.com/MEC solutions. You can also go to the Lanner website, www.lannerinc.com/applications/telecommunication. And you can read the press release that was issued jointly by NoviFlow and Lanner at bit.ly/2tv9aq1.